In this last section of the chapter, we're going to look at loci in the complex plane. In order to understand what we're doing, we're going to have to understand what does this represent. So here we've got the modulus of one complex number subtract another complex number. And we want to kind of get an idea of what this means geometrically. So let's draw a little sketch of the Argand diagram. And we've got two complex numbers, say Z1 over here and Z2 over here. And remember, we can think about these complex numbers as position vectors. So we can think about Z1 as being the position vector from the origin to that point Z1, and Z2 is the position vector from the origin to Z2. Well, remember, Z1 minus Z2, if we're thinking about them as vectors, is the vector that takes us from the end of Z2, so from point Z2 to Z1. So let's do it solid actually. That vector there is Z1 minus Z2 if we're thinking about them as vectors. So when we do the modulus of Z1 minus Z2, remember the modulus just means the length of the vector. So what we're really doing is we're working out the length of the vector that goes from Z2 to Z1. So the length of that vector is basically just the distance between Z1 and Z2. So we can think about Z1, the modulus of Z1 minus Z2, as being the distance between these 2 points. I should probably say that actually it's a little bit misleading putting this vector here and labeling it as Z1 minus Z2. Obviously the position of a vector doesn't matter, but Z1 minus Z2 would actually be if you worked out Z1 minus Z2, it would actually be a point on the Argand diagram which is there. So Z1 minus Z2 is actually a point on the Argand diagram there. But to help us think about this situation with vectors, we can kind of think about that as being the vector that goes from Z2 to Z1. So what we're going to do in this example is we're going to look at a condition which is the modulus of some complex number Z subtract another complex number is equal to a constant R. And we basically want what are all the complex numbers Z that satisfy this condition. So Z1 and R will be given to you in the question. And Z, you can kind of think about Z as the variable that we're trying to find. What can I substitute in to make this work? Well, just thinking about our geometric interpretation of the modulus of one complex number subtract another complex number. This is the distance between Z and the complex number Z1. So we're basically saying we want the distance between Z and Z1 to be equal to this value of R. So if we think about the Argand diagram, and we could plot the complex number that we know, which is Z1, let's say Z1's there, then we're looking for, well, Z just has to be a distance of R away from Z1. So all the points that are a distance of R away from Z1 are going to form a circle around Z1 with radius R. And that will ensure that Z minus Z1, the modulus of that, the distance between Z and Z1, is going to be equal to R. Let's think about a point Z on this circle. Remember, Z minus Z1, you can think about that as the vector that goes from Z1 to Z, so that vector there. And we basically want to make sure that the length of that vector is equal to R. Well, because we've made sure that the radius of the circle is R, then every point on this circle will work. So that's the general principle. Let's have a look at this specific example and work through it. So we're going to look at two different ways of sketching this, this locus. A locus of points, this word locus, basically just means all the points that satisfy this condition. So the first way that we're going to think about this is the geometric way, which we've just done. So thinking about this expression geometrically, we're going to think about 4 as a point on the Argand diagram. And this basically says that the distance between z and 4 is equal to 5. So we could sketch that. If we sketch 4 on our Argand diagram, so we put on the point 4, so let's put 4 there. Then we want all the points z where the distance between z and 4 is equal to 5. So basically all the points are at a distance of 5 away from this point 4. So that's just going to be a circle centered on 4 with a radius of 5. So it might look something like this. And we should probably show that this circle has radius 5, and we can do that by just labelling some of the coordinates of the point. You could draw in a dotted line for the radius as well. So that's going to go through -1 and 9 there as well. So let's just double check that this works. Let's think about the point, any point on this circle, z, because we're saying that z can be anywhere on this circle. And the vector z minus 4 is the vector that takes us from 4 to z. So 4's here, the point 4, z's over there, so it's that vector there. And we want to make sure that that vector has a length of 5. Well, we've done that because we've made sure that the radius has the radius of the circle is 5. Another way of doing this would be to do it algebraically, and it's really important that you understand how to do this algebraically. So the algebraic approach to solving a problem like this is to say, well, let's say that z is a complex number, x plus iy. We want all the coordinates x, y, so all the values of x and y that work in this equation here. So let's substitute in z equals x plus iy. And every single time we do this, we're going to collect together the real part and the imaginary part. So the real part of this complex number is x minus 4, and the imaginary part is y. So we've got a complex number that looks like this. So we need to be able to work out the modulus of this complex number. So this inside the modulus symbol is a complex number. The real part is x minus 4, and the imaginary part is y. Well, you need to know to work out the modulus of a complex number, it's the square root of the real part squared, so that's x minus 4 all squared, plus the imaginary part squared, and the imaginary part is y. And if you're not happy with where that's come from, just think about, we've got this complex number, I don't know where it is, let's say it's over there. The real part is x minus 4, and the imaginary part is y. And the modulus of the complex number is the distance to the origin. So you can use Pythagoras to work out what is that length there. That's what we've done. We just used Pythagoras. Okay, and then we can square both sides of this equation to get x minus 4 all squared plus y squared equals 25. And then you can see that this is the equation of a circle. This is a circle with centre 4, 0, and radius is equal to 5, which is what we had before. So that means as long as x and y lie on this circle, this expression will be satisfied. So it's really common to have a follow-up question using the locus that you just plotted. So here we want the complex number z that satisfy this condition here. So we already know what it means to satisfy this condition. If it satisfies this condition, then it must lie on that circle. But we've got this other condition that the imaginary part of z is equal to 0. So just think about that geometrically. It has to be on this circle, and the imaginary part has to be equal to 0. So that basically means that it could either be there on the circle or there on the circle. because at those points the imaginary part is 0 because it's on the real axis. So perhaps the easiest way of doing this actually is to use the Cartesian equation of the circle. We know that for it to have real part, imaginary part 0, we know that y has to be equal to 0. So y equals 0. So we know basically that x minus 4 squared equals 25. And obviously, because this circle has radius 5, it's really easy to see that's going to be minus 1 and that's going to be 9. So we're going to get x equals minus 1 or x equals 9. Now remember, we're looking for z, not x. So our complex number z is going to be minus 1. And really we've got plus 0i, but we don't need to write that. Or z equals 9 plus 0i, but we're not going to write that. And then for the second part, we're doing exactly the same thing. It has to lie on the circle, but this time we want the real part of z equal to 0. So for the real part of z to be equal to 0 on this circle, we must either be there on the circle or there on the circle to make sure that it's a purely imaginary number. So let's use the equation of the circle again. This time we know that x equals 0. So we can substitute that in to the equation of the circle. So we're going to have 0 minus 4 squared plus y squared equals 25. So we're going to have 16 plus y squared equals 25. So we get y squared equals 9. So we're going to get two solutions, which is what we'd expect. Y equals 3 or y equals minus 3. Now remember, we're looking for the complex number z, which is x plus iy. We've not been asked to find out what x or y is. We've just made that up to help us solve the problem. So when x equals 0 and y equals 3, we're going to get z equals 3i. Or when x equals 0 and y equals minus 3, we'll get z equals minus 3i. Because remember, x was equal to 0.